Imagine you're in the vast, cold emptiness of space. Out here, the rules of nature are different, and the ordinary becomes extraordinary. In this cosmic void, the tiniest building blocks of matter behave in ways that defy our everyday intuition. Picture two tiny particles drifting close to one another, unable to connect, no matter how near they get. Their forces just aren't strong enough to bind them together, so they remain forever apart, like two lonely travelers passing in the night. But now, imagine introducing a third particle into the mix. Suddenly, something magical and unexpected happens. The presence of this third companion changes everything, allowing all three to come together in a way that was impossible for just two. This is the Efimov effect, a remarkable quantum phenomenon where three identical particles can form a bound state, even though no two of them can bind on their own. It's as if the universe rewards cooperation, letting the trio achieve what pairs cannot. Think of it like two people unable to hold hands, but when a third person joins, they can all link together, forming a stable circle. The group becomes stronger than the sum of its parts. This trio, known as an Efimov trimer, doesn't just exist in a single form. Instead, it appears in an infinite ladder of states, each one larger than the last by a universal factor of 22.7. This scaling is a signature of the Efimov effect, and it's unlike anything seen in classical physics. For over 30 years, the Efimov effect remained a theoretical curiosity, a strange prediction that seemed almost too bizarre to be real. But in 2006, scientists finally observed it in the lab, using ultra-cold cesium atoms cooled to near absolute zero. This groundbreaking discovery validated a fundamental prediction about how matter organizes itself at the most basic level. It was a triumph for both theory and experiment, showing that even the strangest ideas in quantum physics can be real. The Efimov effect represents a new kind of universality in physics, a deep principle where the specific details of the particles don't matter. Instead, the same patterns emerge again and again, regardless of the underlying ingredients. As long as the conditions are right, these particles follow the same universal scaling law, no matter what they're made of. This means the Efimov effect can appear in many different systems, from atoms to molecules and beyond. This principle of universality is incredibly powerful. It teaches us that by understanding one simple system, we can uncover truths that apply to vastly different and more complex systems throughout the universe. By studying these simple quantum systems, we gain insight into the behavior of matter in extreme environments, from the hearts of distant stars to the exotic states of matter created in laboratories on Earth. The Efimov effect is like a dance of threes, choreographed by the strange and beautiful rules of quantum mechanics. Each step in this dance reveals new patterns and connections in the fabric of reality. It shows us the universe's hidden rules of assembly, where particles come together in unexpected ways to create new structures. These rules are often counterintuitive, but they are fundamental to how the cosmos is built. The discovery of the Efimov effect opens a new window into the quantum world, revealing the universe's intricate beauty and reminding us that even the smallest things can hold the greatest mysteries. After confirming the existence of three-body Efimov states, scientists were left with a tantalizing question: what about systems with 4 or even 5 particles? The discovery of Efimov states had already challenged conventional wisdom, but the possibility of more complex groupings opened up a new frontier in quantum physics. Theoretical calculations suggested that 4 bosons could indeed form not just one, but 2 distinct Efimov-like states. This prediction was soon put to the test, and after careful experimentation it was confirmed. 4-body quantum states were real, and their properties matched the bold predictions. Yet the 5-body problem loomed large, remaining an unsolved mystery for 15 long years. It became a notorious challenge, one that stumped even the most brilliant physicists and resisted every attempt at a solution. With each additional particle, the complexity of the problem increased exponentially, quickly overwhelming existing mathematical tools and computational methods. The equations became so intricate that even the most advanced techniques seemed to break down. Cracking the 5-body problem was more than an academic exercise. It was crucial for bridging the gap between simple few-body systems and the complex world of many-body quantum physics. Solving it would provide a stepping stone to understanding how simple quantum rules scale up, eventually giving rise to the collective behavior seen in larger, more complicated systems. The 15-year stalemate became legendary in the physics community, drawing in brilliant minds from around the world, many of whom would retreat defeated. only to return and try again. The calculations were monstrous, the obstacles immense, and the path forward was shrouded in a dense mathematical fog that few dared to enter. Solving the five-body problem would require not just incremental progress, but a leap in both computational power and theoretical insight, a true breakthrough in the field. The question echoed through physics departments worldwide: what is the universal rate at which 5 bosons can form a bound state? The answer remained elusive, a riddle that challenged the very limits of quantum theory. Ultimately, answering this question would demand more than just persistence. It would require a fundamental breakthrough, one that could reshape our understanding of quantum systems forever. Why does adding just one more particle to a system, a seemingly simple step, suddenly make the problem so much harder to solve? What is it about that extra particle that transforms a manageable puzzle into something that feels almost impossible? The answer lies in what scientists call combinatorial explosion, where the number of possible interactions and configurations grows exponentially with each new particle. With just 5 particles, the number of ways they can interact skyrockets, creating a dense, tangled web of connections that's almost impossible to untangle by hand. Each particle is described by a quantum wave function, and together, they form a colossal, interconnected entity that's far more complex than the sum of its parts. Calculating the behavior of this system is a nightmare, with equations that quickly become too intricate and unwieldy for even the most powerful computers to solve directly. The Efimov effect, which emerges in these systems, is a threshold phenomenon that demands immense experimental and theoretical precision to observe and understand. Any small error, whether in measurement or calculation, can cause the entire solution to fall apart, making progress painstakingly slow. Physicists needed to find a universal recombination rate, a key value buried deep within layers of computational complexity and mathematical abstraction. The 5-atom system sits right on the precipice between the world of few-body physics and the vast, chaotic realm of many-body physics. Solving it required not just faster computers but clever algorithms, creative teamwork, and a brand new mathematical idea. The problem demanded a perfect storm of ingredients, technology, insight, and persistence to finally crack the code. In the end, this was the first step into the true wilderness of quantum complexity, where every new particle opens up a whole new world of challenges and possibilities. Enter the heroes of this story, a team of physicists at Purdue University. Led by Professor Christopher Greene, they tackled the 5-body problem with fresh perspective. Greene assembled a dedicated team, combining experience with computational skills. The team included Jia Wang, a brilliant postdoctoral researcher. Their strategy was threefold: harness modern supercomputers, develop new algorithms, and achieve a theoretical breakthrough. They embodied the spirit of modern scientific exploration, like mountaineers planning an assault on an unclimbed peak. Their laboratory was not of test tubes but of equations and computer clusters. They meticulously prepared their mathematical and computational tools, their goal to finally solve the 5-body Efimov puzzle. This collaborative environment is where modern science thrives. It was a blend of seasoned wisdom and innovative new techniques. The Purdue team needed more than desktop computers. They needed supercomputers. They turned to Purdue's community clusters, simulating phenomena too complex for physical labs. These supercomputers became their virtual laboratory for quantum physics. The 5-body problem was so complex that even supercomputers needed intelligent management. The team used parallel processing, breaking calculations into smaller pieces for simultaneous processing. The scale of computation was immense, consuming millions of CPU hours. They ran simulations for months, exploring the vast space of the 5 particles wave function. This reliance on supercomputers highlights a shift in theoretical science. Computation is now a third pillar of science alongside theory and experiment. Supercomputers act as a mathematical microscope, revealing the consequences of theories. They are digital hadron colliders, smashing numbers to reveal nature's secrets. The breakthrough came from a moment of profound theoretical insight. Greene's team developed new mathematical techniques, translating the 5-body problem into a manageable language. They devised a new way to write equations, sidestepping computational roadblocks. The core innovation involved representing the hyper-radial potential, filtering out mathematical noise. This new framework reduced computational resources needed, making the problem solvable. By changing the mathematical language, they made the question easier to understand. The new tools can now be used by other physicists for complex quantum problems. It's a gift to the scientific community, opening new fields of inquiry. This is the beauty of theoretical physics. New methods open up new questions. After months of computation, the moment of truth arrived. The supercomputers delivered an answer, the universal scaling factor for 5 bosons. They found the magic number that eluded physicists for 15 years. The result was a specific universal ratio, a new rule in the quantum playbook. The discovery connected few body systems to many-body physics. The publication sent excitement through the physics community. It was a landmark achievement, demonstrating a powerful new capability. The combination of insight and computation broke a long-standing barrier. For Greene's team, it was validation of their approach. They ventured into the quantum wilderness and returned with a map. Solving the quantum puzzle has implications from labs to the cosmos. Experimental atomic physics can now test precise predictions with ultra-cold gases. The discovery deepens our understanding of universality, a powerful tool. Lessons from a handful of atoms apply to exotic systems like neutron stars. Understanding particle combinations is fundamental to chemistry and materials science. The mathematical techniques can explore other complex quantum systems. This breakthrough is about understanding the nature of matter itself. By pushing calculation boundaries, we get a clearer picture of fundamental rules. The 5-body problem was a frontier, expanding our knowledge and perspective. The 5-body Efimov puzzle illustrates the scientific process. It begins with a prediction, followed by decades of effort, leading to new questions. Solving it opens up new questions and equips us to tackle them. This discovery shows daunting challenges can be overcome with ingenuity and technology. Solved puzzles strengthen our foundation of knowledge, leading to future innovation. We can't predict future technologies from this understanding, but history shows deeper understanding leads to innovation. The quest to understand quantum rules is deeply human, driven by curiosity. The solution to the Efimov puzzle is a step on the journey to comprehend the cosmos. It's a journey that brings us closer to understanding the universe and our connection to it.